am I audible to everyone? Please put yes in the chat. If I am audible, please put yes in the chat. Okay, thank you, Kirtana. Before we start, I will share my screen. Okay, you guys can see my screen, right? Please confirm it in the chat. You can screen my screen, can see my screen, then put yes in the chat. Yeah, okay. Okay, thank you. So, once again, hello everyone, and warm welcome to day 9 of our Data Science and AI add-on certificate course with Industry Internship. Thank you all for joining today. As you know, I am Alphy Mathew, research engineer at Alphy Solutions Limited. And today, we move into one of the beginner-friendly machine learning algorithm called our next algorithm, that is the decision tree. Okay, so a decision tree is nothing but a machine that learns using if else rules automatically. Okay, it's just like if else rules. So the same kind of rules we naturally use in daily life. For example, if it rains, then I will take an umbrella. Or if it not rains, then I will not take an umbrella. Like that, by framing if else rules, we will be taking the decision. Either the loan can be approved or not. Or like that, the classification problem will be addressed using such if-then rules. Okay, so decision tree follows the exact same logic but in a structure and a step-by-step way. So today we will understand how a decision tree decides what question to ask, or how to split the data, or how to predict the outcome, etc. So let's begin our day 5 of machine learning, that is decision tree algorithm. So as I already said, a decision tree is one of the simplest and most popular algorithm used in data science. Okay, so the reason people love it is because it works almost exactly like human making decisions in real life. So it can be this decision tree can be both used in classification and regression. And in our session, we will be discussing how the decision tree works with if-else rules in classification. Okay, so for example, here there is an if-else rule is given here. What it says: if the price is less than 50,000, then we will check if the brand is Dell, then I will buy the computer or the laptop. Okay, else I will not buy the laptop. Suppose our problem is buy a person buys a laptop or not. Suppose it is our problem. Then what's the if else rules what we frame in our mind like this. Suppose the person is thinking like if the price is less than 50,000 and the brand is Dell, then I will buy the laptop. If price is less than 50,000 but the brand is not Dell, then he will not buy the laptop. Also, if the price is not less than 50,000, then he or he will not buy the laptop. So like this, in decision trees, we will frame if-then rules by the help of decision trees. We will create decision trees. It is a data structure like trees-like structure. We will create it. From that tree-like structure, we will find if-else rules, and using that rules, we will classify the objects. Okay. So now we need to know more technical details about what is decision tree, what are the parts of the decision tree, etc. So here we are focusing on uh, what are the structure or what is actually decision tree is. Okay, so the decision tree has few main parts that are easy to understand. So this is the structure of a decision tree, the first figure. Okay, at the very top of the tree, it will be the root node. Okay, at the very top of the tree will be the root node, which is the first question the model asks and where the decision process begins. Okay, here the model will be starting its journey. Then below the root node, there will be internal nodes, which are the other questions asked along the way. Each one or each internal node checks a specific feature and helps split the data further. In between the nodes, there will be branches. So these connections are the branches. Then these branches are connects those nodes, the root node or the internal node, and these branches are these branches represent the possible answers or conditions that each node can cause, like yes or no, or like male or female, like that. The whatever the distinct values a column or an attribute can take, that will be represented by the branches. At the bottom of the tree, at the end of the tree, we will be having the leaf nodes. Okay, at the end of the tree, we will be having the leaf nodes, and these leaf nodes will be the class labels. Okay, the leaf nodes will be the class labels. So it is like a flow chart. You can map it like a flow chart. So think like for example, here we can see a decision tree. I will put it in slideshow. This one is the one example for decision tree. This weather time hungry decision tree. So let's look what this tree explains. Okay. So imagine you are deciding whether to walk or take the bus. You need to decide whether to walk or take the bus. So we have created a decision tree using this algorithm. Suppose you have created it. Then how you will make decisions? At the top it will be the root node. That is the first node will be the root node, which asks the question. What is we are asking? Suppose I am asking like, is it raining? I am asking like, what is the weather? That is, it raining? Then what will be the branch? Raining means it will be gone through this branch, and it is coming as a direct decision that if it is raining, I will be going by bus. Okay, then in this decision trees, this is the root node. The first one is the root node, and these blue colored are the intermediate node, and these orange colored or the yellow colored are the leaf nodes. Leaf nodes are the end nodes, and leaf nodes do not have branches, and the leaf nodes represents what the class label or the predicted class. So this flowchart style structure makes decision tree very easy to understand because you can clearly see how each answer leads to the final choice. Suppose if the weather is cloud and if you are hungry, means if the weather is cloud and you are hungry, yes, then you will be walking. So like that, through traversing through this decision tree, you can classify the class labels for the particular problem. Then why it is called a tree? Because the structure literally looks like a tree turned upside down, right? A tree, a natural tree turned upside down. The topmost part is the root node. So from there the branches go downwards, and the bottom part is the leaf nodes. The shape and the flow look very similar to a real tree, just inverted. So decision trees are very popular because the logic they use to interpret. That is the if then rules. Very simple logic it is using. So it is easy to interpret. Use. Now we need to study to how we can create such trees from the our data set. Now from the data set, we need to create this like of structure. Then only our algorithm or our model can predict like what is the decision. So we need to create it. Right? Then how we will create this decision trees? That is our next focus. So this is same as what we have discussed. Why the tree is known as a natural tree, because it is like the inverted tree. It has root at the top, branches are in the middle, intermediate nodes are there, and the bottom level nodes will be the leaf nodes. Okay, the same structure diagram given here. So this is another example of decision tree. Here you can see that our problem is predict heart attack risk. Okay, we need to predict the heart attack risk based on some attributes. Our attributes are weight, age, smoker. Suppose attributes means our data set columns. Weight is there, age is there, smoker is also there. So suppose we have taken that data set and we have created that decision tree, then we are trying to interpret this decision tree. It's very easy. You can yourself interpret it, but for more understandability, I am just explaining it once again. Here, if the age is less than 18, this tree will check the weight of the person. Okay, so here the weight is the another decision node or the internal node, because another decision is made here. Okay, if weight is less than 60, then the model predicts he or she is having low risk at the heart attack. If the if the weight is greater than 60, then the model predicts he or she is at high risk of heart attack. Exactly like that. If the age is between 18 and 30, then it is at low risk. Then coming to age is greater than 30 and here she is a smoker, then there is a high risk of heart attack. And if he or she is not a smoker, then there is a low risk of heart attack. So inside this tree, we can see small trees. That trees are known as subtree. Okay, so this is exactly how the human think when making decisions. We don't look all the factors at once. We check each conditions one by one and we will take decisions. So decision trees are very popular because of it is so easy to understand, easy to explain, and works like real life reasoning. Okay, so we are now knowing how we will create this decision tree. Our problem is we only have the data set. We need to create such decision trees from our data set. That's our aim. So for example, in our case, what we need to predict the bank will approve loan or not. That is our problem, right? So a decision tree will be we keep splitting the applicants into smaller, or splitting the data set into smaller groups based on the features, sometimes based on income, sometimes based on credit score, sometimes on age, etc. So how exactly this algorithm build the tree? That is, first the model looks at all the features in the data set and tries to find the best attribute to split the data. Okay, so then how this best attribute is found from the data set? This is done by finding something called attribute selection measures. That is ASM, attribute selection measures. There are so many attribute selection measures available. That is Gini index, then entropy, information gain. And in our session, we will be seeing entropy and information gain. Using that, we will be looking into how the tree is built. Okay, so the steps are given here. The basic idea is that when we will take all the features from the data set, that all the column in the data set, we will find the most important column from the data set by using any of the ASM measures like entropy or information gain. There are mathematical formulas. We will find the best attribute, and according to that attribute we will start building the tree, and iteratively we will build the tree until either one of the condition is met. Either all the data points in the branch belong to the same class, or no more attribute left to split, or there are no more data or no more row to divide. So until any of these three conditions meets, the same process of finding the best attribute and splitting the tree or creating the tree will be done continuously. I know that I have been explaining it very in a short way, but no worries, we will be seeing how this is built step by step in upcoming slides. Okay, so here it's only explained about the steps in the what building decision trees. So in order to understand it clearly, we can go through a small data set and we can apply this the steps we have seen one by one clearly. Okay. Suppose we have a mini data set here with only 8 observations. You can see 8 rows. What are the columns it has? It has ID column, temperature column, humidity column, windy column, play column. Just for a quick query, in this three columns, what this 1, 2, 3, 4, 5 columns are there. If I ask, in this column, what do you think? What are the input variables and what is the target variable? Target means the output variable. Yes, correct. Our target or the output is play. Yes, correct. So, what we are planning to do is that we are going to create the decision tree from this small data set. Our aim is to understand the steps in the decision trees. Okay. So here we have important three input variables. ID can be ignored. You know that in non-ID also we have dropped it. So just ignore this ID. So the main important input features are temperature, humidity, windy, and our target is play. Okay, temperature has three distinct values. What? Hot, mild, and cool. Okay, then humidity have two distinct values, high and normal. Windy have also two values, false and true. And play is like two labels, yes and no. Then what is our problem is, according to these attributes, whether the child will go for outside for playing or not. That is our problem. We need to predict yes or no for play. That whether the child will go for play or not. That is our classification problem. So a decision tree asks a series of questions about the features to reach the. We already know that is the humidity is high or the temperature mild or the wind is false, etc. The decision tree is trying to answer the questions. So we need to make the decision tree from these attributes. Okay. For that, what we want to do is the first step we want to do is we will calculate the parent entropy. Entropy is one of the attribute selection measure to find the most important feature from the given data set. The most important column from the given data set. So we will find the data means the complete data set entropy. Okay, then what is this entropy means? Then or the value of entropy, what the meaning it is. Okay, so if the data is mixed in the sense, suppose we have no and yes mixed values, then such cases the entropy will be very high. Suppose if you are getting an entropy equal to 0, it means that all the values are in the same class. For example, look here. There is a set A. This is an impure set because it has different values A and R. It is a mixture. Okay. For this, the entropy will be high. Then look at here A. All are A. Means it is pure. Then such cases, the entropy will be 0. Okay, here it is also pure because only R is there. Then for such case, if we find the entropy of this one, it will be 0. So entropy is the measure of impurity or randomness. We can say that higher the value of entropy, higher will be impurity. Impurity in the sense the mixed values. Okay. Then mixed classes. Impurity means mixed classes. Purity means single class. Okay. So if entropy is high, meaning what impurity is there, entropy is low, meaning in somewhat low. If entropy is 0, then pure. Okay, that is the idea of entropy. Then first we want to find parent entropy. For that, we need to count for how many yes or no in our data set, how many yes labels and how many no labels. That is the output class labels count we need to find first. So we have, as you can count it from the data set, we can see that we have 5 yes and I think it's 3 no's. Okay, 5 yes and 3 no's are there in this cataloged records, right? So 5 yes and 3 no's. Then we need to find the entropy. The formula for entropy is minus negative of probability of yes, yes in the sense the class label yes, probability of yes into log to the base 2 probability of yes minus probability of no into log to the base 2 probability of no. So it is purely mathematics, that is probability and the log calculations are given here. You are not going deep, but to understand what is happening here, I will explain it. Okay. So here we need to find probability of yes and probability of no. You already know how to find the probability. Probability is yes is what? 5 by 8. Why? Total number of yes is 5 and total number of observation is 8. So probability of yes is 5 by 8. Then probability of no will be 3 by 8. Then substitute it in the formula. Then we will find 5 by 8 into log to the base power 5 by 8. Then 3 by 8 into log to the base of 2, 3 by 8. Like that you need to calculate it. And after calculations of this, we will find that the entropy of parent entropy, the entropy of the entire data set is 0.954. Okay, 0.9, it's approximately equal to 0.954. So our parent node entropy is 0.95, which means that the data is mixed here and also it needs to split further. You may think that we already know that this is mixed, then why we are finding this entropy? Why? Because computer do not see this, right? Computer do not have any eyes. We are seeing it and we know that no, yes. Computer need to find this entropy to find whether it is mixed or not. Okay, so it is as the first step, it is starting with the entropy of the parent node. As we can see these things, we know that this is the mixed one, but computer needs to find it with pure mathematics. Okay, this is the first step what we want to do. We need to find the entropy of the parent node, that is data. Okay, the formula is given here. Now in the second step, what we do is that we need to check if splitting the data based on a feature reduces the impurity. Now we found that our data set have impurity. So next we need to check splitting with temperature reduces the impurity, or splitting with windy column reduces the impurity, or splitting with humidity column reduces the impurity. We need to check these 3 scenarios. For that, we will find the information gain for each of the attribute. We will find IG, information gain for temperature. We will find information gain for humidity. We will find information gain for windy. And the one with the highest information gain will be the first node of our decision tree. That is our idea. Okay, it's a basic idea, and now I am going to explain the maths behind that. Okay, so first we are going to try to split on the first attribute temperature. We are going to find the information gain of the attribute temperature. So we are taking over the temperature column. There are 3 distinct values. You can see hot, mild, cool. Then how many hot have yes? It is only 1. How many mild have yes? It's only 2. S in the sense play equal to S. Okay. Then cool, how many cool have play equal to S2? Just to count from the data set. Then exactly the same we are filling with the no. Okay. So total hot incidents are hot weather instances are in 3. Total number 3. Mild we have 2. Cool we have 3. Okay. So it means that the temperature column has 3 groups. The first group is hot group, second group is mild group, and the third group is cool group. So first we need to find the entropy of temperature equal to hot, the entropy of temperature equal to mild, and the entropy of temperature equal to cool. That is our So we know that in this first step, we need to put P of S into log to the base P of S minus P of no into the same formula. Here the value will be different. For hot, how many S are there? 1. Then total observation, how many? 3. So the probability is 1 by 3. Okay. Then how many no are there in hot? 2. Total hot, how many are there? 3. Then the probability of no in hot is 2 by 3. Just substitute the value, apply in the formula, and entropy of hot, we are getting approximately 0.918. Okay. Then again we are finding entropy of mild. Okay. In entropy of mild, you can see that entropy of mild, it's directly 2 by 2. It is coming 2 by 2 because there is no in entropy of mild. Sorry, in mild. There is K equal to no is absent in mild. It's only yes. So the probability when coming to 2 by 2, it's 1. It's saying that the mild case, the entropy is 0. That is, for temperature equal to mild, the P there, it is the pure set. It has no mixed values there. Then the same entropy we will find for cool. Temperature equal to cool. Number of observation of S in cool is 2 by 3 and no in cool is 1 by 3. So we will substitute there and we get around 0.918 for temperature equal to cool entropy. Okay. Now we have computed entropy for temperature for each group, hot group, mild group, and cool group. Now we need to find the weighted entropy. We only need one entropy, right, for entire temperature column. For that, we need to find the weighted entropy. To find the weighted entropy, what we are going to do is that total, we combine the three entropies using the size of each group. Hot group size means 3. Out of 8 observation, how many hot are there? 3. Then how many mild are there? 2. How many cool are there? 3. So total probability of P of hot is what? 2 by 8. P of mild is what? 2 by 8. And cool is 2 by 8. Just multiply that with the corresponding entropy of hot, mild, and cool. It is given here. 3 by 8 means probability of hot into entropy of hot. 2 by 8 means probability of mild into entropy of mild. Entropy of mild. And in probability of cool equal to what? 3. 3 by 8 and into the entropy of cool. Okay, then we will get the weighted entropy of temperature attribute, and that is somewhat around 0.688. Okay, now we have the entropy of temperature node and we have the parent entropy that we calculated in step 1. We have the parent entropy and we have the entropy of temperature node. Okay, temperature node. Now we need to find the information gain. Information gain is the entropy before split minus entropy after split. That is parent entropy minus entropy of temperature. So our parent entropy was 0.954 and our temperature entropy was 0.688. So the information gain of temperature attribute is 0.266. Okay, so now we have found the information gain of what? The temperature attribute. Similarly, we need to find the information gain for humidity and also for what? The windy column. The same steps. You need to count how many high are there in S, then how many high are no, then total high observations 4, then how many humidity normal yes are there, how many humidity normal no are there, then how many normal observations are there, normal instances are there. We counted it and there are only 2 go because 2 distinct values, high and normal, right? So for high group, we have found the entropy of high, substitute the values with the probabilities and then find the entropy. And also for normal, we are finding the entropy and we find the weighted average. that is weighted entropy of humidity by total probability into the entropy of particular class, entropy of high into probability of high, and then entropy of normal into probability of normal. We found that 0.95. Then we will find the information gain, that is parent entropy minus this particular entropy of humidity, and we will get that 0.049. So we found the information gain for temperature column. We found it for what? Humidity column. Now again we need to find it for windy column. The same step, but we need to find it for windy column. So how many attributes are present in the data set? Input attributes are there. For each input attribute, we need to find information gain. Okay. Then what we for our windy column we have got 0.158 as information gain. Okay, the same steps. I am not repeating it again and again. Here we have found for information gain of windy column is around 0.158. Okay. Now next we need to compare this. We have only 3 input variables, so only 3 information gain value. Then the attribute having the highest information gain will be the winner. That it will be the most important attribute. So here our winner is temperature column, because others are only about 0.1 and 0.0 around that. Our temperature column has the highest information gain. So our decision tree's first node, our root node will be temperature. So we have drawn our root node as temperature, and the distinct values of root node will be the branches. What were the distinct values? Hot, mild, cool. So 3 branches came there. Okay, so this is the first split in the tree. Okay, this is the first split in the tree. So here you need to remember one important thing, that is every time we split the tree, the data set based on an attribute, each branches forms smaller mini data set. I repeat, every time we split the data set based on an attribute, then each branches forms a smaller mini data set. Okay, for example, here in this temperature node, our entire data set will be there. But in hot branch, the hot subset only will be there. In mild branch, the mild subset only will be there. In cool branch, the cool subset only will be there. Okay, so from here onwards, the algorithm looks only at the rows inside the subsets, not the entire data set. Okay, for the root node only the entire data set is taken. If you are going to split the tree again and again, then the subset is taken in consideration. Only in the hot, only in the mild, and only in the cool. So the steps are repeated again and again. What steps? The entropy calculation, the information gain calculation, the highest attribute IG calculation is done again and again in the each branch, in hot branch, in mild branch, and in cold branch. Okay, we are going to see how it happens. So here in this image, I have split the data set, and the subsets are given in the branch to for you guys to get an idea how the entire data set is divided as or split as subsets according to the generation. Okay, you can see that the hot here at the first time the entire data set with 8 observations were there. But in the hot branch, only this much data set will be there. That is with ID 1, 2, and 8, only 3. Okay. Then in the cool branch, only temperature cool will be there. In the mild branch, only temperature mild will be there. Okay, so at this stage, each subset becomes the mini data set. So from here onwards, for this hot branch, this is our data set. For mild branch, this is our data set. And for cool branch, this is our data set. Okay, so the algorithm, from here the algorithm will repeat the same process again and again. Here also we need to find again the entropy for each one and information gain for each one, the temperature, humidity, windy, and again, not for temperature, humidity and windy, and again we will find the importance from those two and we will split there. Like that, the splitting is going to continue from the or in these subsets. Okay, so we can try to complete this tree. Okay, here we will go directly into the mild branch. Okay, first our focus is in the mild branch. You can see that in the mild branch, all the class labels are yes. You look play equal to yes, yes. In the mild branch, play become pure. Pure means both are yes. That is, there is no mixed classes here. Both says it is yes. So here there is no mixture of yes or no. There is the subset is pure. We can say that this data set become pure in the mild branch. That is, if we calculate the entropy of this branch, it is zero. You know that earlier we have calculated the entropy of mild and we got it as zero there. Okay, it means that that node is pure. When the entropy becomes zero, one of our condition is met to stop the tree. Stop the tree in the sense start splitting the tree. So there, in this case, we can replace the node as the leaf node with the class label as yes, because all are pure. Both says it is yes, so replace it with the leaf node yes. Leaf node is represented as an eclipse shape. Okay, so here for the branch temperature equal to mild, is always yes. So this is directly going to our decision, that is, if temperature is mild, the child goes for play, or the child plays. Okay, so for this branch, we do not want to split further because the data set was pure, so we replaced it with the leaf node. Okay, now we need to go to the next branch. Next branch is the, suppose we can take the temperature equal to hot branch, this one. Okay, here in the hot branch, again we need to calculate the entropy and the information gain. So when we look at this hot branch, we have how many yes are there? One yes is there and two no is there. Okay, so it is mixed. That is impure. We need splitting here. Okay, at this point, how many attributes are there to split? Two attributes. That is humidity and wind. Okay, so we need to calculate the entropy for the hot subset. We will find the entropy of this data set and this data subset, and then we will find the information gain for humidity, and we will find the information gain for windy. Okay, then select the attribute with the highest information gain. Exactly, we done the maths we discussed earlier. Okay, the one with the highest information gain will be the most important one. Okay, when we find the entropy of humidity, we can see that the information gain will be pointed to 1. That is the highest value. In such cases, we do not want to find for windy because humidity itself is a high value. Then windy is not found here. Okay, so when we track the IG values, that is the information gain values of humidity and windy, humidity got around 1, and it says that it is the highest information gain value. So here we will take the decision that at the branch temperature equal to hot, the next split we need to give is on the humidity column. That is the humidity attribute. Okay, so that is we are going to do next. Look, we have replaced that with humidity, and then distinct values in the humidity columns were high and normal, right? So the high observation going to here, the subset data set, and the normal instances go to the next subset in the that branch. Here also it's very easy. You can see that when we look into the play labels, here it is also pure, right? Both are no, it's pure. So we can replace it with a leaf node. Here also only one observation, only one yes, that is pure. No mixed classes are there. Then we can here also we can replace it with yes. So our decision is made here. When temperature is hot, we need to check humidity, and if humidity is high, the children will not go for play, and humidity is normal, the child will go for a play. Okay. So here just splitting it, finding the important attribute, splitting according to that attribute, looking the purity, and according to the purity, we are replacing it with the leaf nodes. Now the next branch is the cool branch. Okay. Our cool branch. Then what happens to our cool branch? This is our cool branch. We haven't added any split here. This is incomplete here. And this is our cool branch dataset. Okay. Okay, this is our cool branch dataset. You can see that. So here in the cool branch, you can see that there are 2 yes and 1 no. 2 yes and 1 no. So this is a mixed subset. It is not pure. So we need a what? We need a split here. So we have two attributes to split, humidity and wind. Okay. When you look here, you can see that humidity is, the column humidity is pure, all are normal. Then what is the meaning to split it with humidity? There is no meaning to split with humidity, right? Because in humidity column, all are normal. Then how we will split? We add the here humidity and also humidity is taken here. Then the remaining attribute is windy. So we can replace here with windy. It's correct. Look, I have replaced it with windy. Okay, here with windy, there are two attributes, two distinct values are there, false and true. So we are splitting this data set into windy equal to false and windy equal to true. Here, for the windy equal to false branch, there is no complications because it is only one one attribute is there. So it's very easy. It is pure. We can replace it with the label. Leaf node. Yes, this class label is as the leaf node. But look here. Here in the windy equal to true, what is that? There is one yes and one no. There is a tie. Then how the decision tree will make the decision? That we need to understand. That's very simple. What the decision tree look is that he will look into the parent subset. Okay, for this node, the parent data set is this one, right? It will look for the majority class in the parent set. What is the majority class in the parent subset? Yes. Most of the observation in the parent says yes. Place equal to yes. There are two yes and one no. So the majority is yes. So what happens? Replace it with yes. Why? Because here only one no and one yes. Tie is there. We need to break the tie. To break the tie, it will go and look in the parent just before subset. And that subset, which will be the majority one, that will be replaced here. That is yes. So this is how our entire tree is built. Okay, so in simple words, the tree says that here in this point, in the leaf nodes, are the endpoints. Endpoint means at the leaf node we are not having any splits. That means when the data set is becoming pure, we are stopping the iteration. Okay. Not only in some cases the iteration stops, in other conditions also, and that conditions are either we will finish up with the attributes. If all the attributes in the data set is over, then the tree growing finishes. Second thing is that when the data set become pure, it will finish. And third one is that when the number of rows becomes 0, that is this observation. No, if there are no more attributes to split also, or no more attribute to split in the subset also, what happens? The splitting or the growing of the tree stops. In our case, we have built a small tree with the two internal nodes, that is humidity and windy, one root node temperature, and leaf nodes with the class labels yes and no. Okay, so here you know how to interpret this tree. It's very simple. If temperature is hot, humidity is high, children not going for playing. If temperature is hot, humidity normal, child will play. Temperature mild, child will play. Temperature is cool if windy equal to false. That is, if it is not windy, the child will play. If it is windy also, the child will play. Okay. So remember, a decision tree keeps splitting the data recursively. That means the same process again and again on every child subset. But the splitting does not continue forever. It stops as soon as any one of the condition is met. So always remember, if any of these condition is met, the splitting will be stopped. Okay, any one. The first condition is all tuples belong to the same attribute value. Tuple means rows. The row, other name of tuple is row, the observation. Okay, that is the all the nodes or all the rows in this our data set is belonging to the same class, then that is pure class, then the split stops. Then if no more attribute to split, that is no more attribute or column is there in our data set to split, in that time also the tree growing ends. Then other case is that there are no more instances, no more rows in the subset to split. That is the branch become empty. Such cases also the growing of the tree will be stopped. So in our data set, the third condition didn't occur. There is no more instances. This doesn't occur. Okay, in our cases, we were the first case where we were not having any more attribute to split because we only had three. We used three, it stopped. And also in the mild branch case, what happens? It become pure and there is no splitting here. So these two conditions occurred in our cases, but there are some cases where this third condition is there. Only one of the condition is met, the splitting stops. Okay, so from here, this tree, we will be framing rules, natural language version rules, like how the people says, like if the temperature is mild, the child goes out to play. If the temperature is hot and the humidity is high, the child stays inside. If the temperature is hot and the humidity is normal, the child goes out to play. And if the temperature is cool and the child goes out to play, whether it is windy or not. Okay, so exactly as a human rules or human decision making, we have built rules in the form of if-then rules from the decision tree. This is exactly how the decision tree grows and works. Okay, now we need to see the practical part of decision tree. You may be thinking we have seen so many maths, so many steps, but coming to the practical part, it's very hands-on. What? Just import the decision tree, do the training, edit, find the accuracy score. That's only in the practical session. But in order to understand what is exactly happening inside the trees, you need to go step by step. Okay, so we are going to our loan prediction case study. So remember that for each fresh sessions in the collab, you need to rerun the codes, you need to re-upload the dataset. So when you try out, please remember to rerun every cells. Okay, so here I am also, as usual, I am using the pre-coded versions, and to use the decision tree, we need to import decision tree classifier. Okay, we need an import statement, and in the library session, we will import it as, look here, from sklearn.tree import decision tree classifier. So the entire algorithm is imported here. So inside that, we need to give, first we need to create the object. Okay, this is our object. We are creating the model object, and inside that you can see something interesting, random underscore state equal to 42. Can anybody guess where you have seen this? Anywhere you can recollect you have seen this random state in our sessions? Any guess? We have used this random state before. Can anybody guess in which part of code? I will give a clue, like we have used random state in pre-processing steps. In which pre-processing step we have used the random state? Yeah, yes, Vinaya, very good. Splitting the data for training and testing set. Yes, train underscore test underscore split. Sanjay, correct. Yes, there we have seen this random state. In decision trees also we have random state. Then why decision tree needs the random state? We need to understand that. So random state is just a number to make sure we get the same result every time. Exactly what we did in split also. So to get the same speed every time, we given the random state. Here also in the decision tree, we are giving random state to get the same result every time. Then if we don't fix this number, the tree may build slightly different each time. Okay, so the random state is used in decision trees to make sure the result stays the same every time we run the code. Run the code. So you may be wondering, why does the result change all time? Every time this is max, right? Then why this result change all time? So that is because decision trees involves randomness inside the algorithm. For example, let me explain in a simple way. A decision tree has to choose which feature to split, or which is the important feature, like that. The decision tree needs to choose the feature to split, wires to split, and it will, sometimes, if suppose you think like that, sometimes when two splits look equally, if two attributes are getting same information gain, then which will be taken? If windy and temperature had the same information gain, and that both are the highest information gain, then who will be the node? There is a randomness there, no? So, to control that randomness, we are giving this random state. Sometimes if you are not giving that random state, what happens? In first run, it will be taking temperature. In the second run, it will be taking windy, because both having same information gain. In such cases, to make it make the tree to be created same in every run, we are giving a random state number here. Okay, I think you got an idea why random state is used here. But simply to make sure the result stays same every time. That is, make sure the tree created is same every time. Okay, then what we want to do, we need to train the model using the object. Okay, that's using the fit function. We will giving the our x train and y train there. That is our training data set, and we will give them, and we will be training the decision tree model, and the created tree, it will be stored in DT model. DT underscore model, and to that tree we will be giving our x test to predict values, and that predicted values of our models will be stored in DT underscore pred. And we will give the final correct answers and our predicted answers to the accuracy score, and we can see that it is very poor, that is 0.66 something, compared to other algorithms we have seen. Okay, so we found the accuracy score. So when we compare with other models, we can see that the accuracy score is low. It does not mean that decision trees are bad. Okay, there are many techniques used in decision trees in which we can tune this, like pruning, post pruning, pre pruning. Its decision trees itself is a very big topic, but for you to understand all the other topics, the basics are much important, and we have covered all the basics what happens in the decision tree classifiers. Okay, so in the next report you already know now that our confusion matrix, again I have printed that we have 17 and 63, that is 17 plus 63 correct predictions and 18 plus 22 incorrect predictions. True negatives and true positives, false negatives and false positives. I think you all guys know how it is interpreted, so I'm not explaining it once again and again. It's already explained in past two sessions, so try to interpret it as you are on. Okay. Now I have printed all the accuracies here one by one. First, print statements. SVM linear, the accuracy of SVM linear model. The KNN, the accuracy of KNN model. DT for decision tree, accuracy of decision tree model. Then SVM RBF, SVM polynomial, SVM sigmoid. Just printed the accuracy once again. And in our case study, we found that SVM linear and SVM, I think RBF is having around 0.81 accuracies with our preprocessing steps with our data sets. Okay, so in machine learning, we always try multiple models and we compare. That is the process. Okay, there are many advanced techniques to tune these accuracies. As I already mentioned in the previous classes, like there are parameter tunings, there are regularizations, there are ensemble models, there are cross-validation techniques, there are feature engineering, and so many techniques are there to tune this. And we will be comparing all the algorithms, and we will be taking a decision which algorithm is better for our data set. Okay, so before we end, let's quickly rewind the entire one case study. What we did is that we downloaded the raw data set, we cleaned it, we handled the missing values, we encoded the categorical columns, we scaled the numerical features, then we splitted the data set into train and tested. Then what we tried, three algorithms, three classification algorithms. There are many more classification algorithms available. Logistic regression is there, and then name-based classifiers are there. If interested, you can go and research and increase your skill and increase your knowledge in such algorithms. Okay, if we can also try that. Different types of name-based are there. So many algorithms are available. So in our case, we compared only three models and understood which one was better in our case. Okay, so doing by this simple but simple case study, we learned the basic machine learning workflow, that is pre-processing, training, prediction, evaluation, and comparison. Okay, so now we can have a quick knowledge check as we do every day. So we have only three questions. First question is like, a decision tree is trained on this data set to predict pass or fail. Okay, suppose I will put it in the chat. Okay, suppose you have a data set. Okay, suppose you have a data set and you need to predict pass or fail. The attributes are attendance, internal marks, and result. During training, the algorithm chooses attendance as the root node. Why? Why attendance become the root node? Options. Option A, attendance column appears first in the dataset. Attendance column gives highest information gain. Attendance has no missing values. Attendance column is numeric. Why the attendance column become the root node? Aparna is saying it's me, others. Yes, correct. B. The information gain. The attribute with the highest information gain will be the split attribute. The most important will be the root node, next important will be the second internal node, like that. Okay, yes, correct. Option B is the correct one. And the next question, during prediction, a decision tree, fill the sentence. Okay, it's very simple. During predictions, decision tree checks all paths, chooses the shortest path, follows one path from root to leaf, uses average of all leaves. How the decision tree predicts the labels. Sanjay says it's asleep. Any other answers? C is the correct answer. I think you may be confused with the question. It's very simple. If you have a decision tree, how you will predict? How you will predict? Suppose our input is like temperature is hot, humidity is high. Our input is like temperature is hot and humidity is high. This is our input. We need to predict whether the child plays or not. Okay, plays or not. This is our scenario. Then this is the new input we need to predict. We have the decision tree. What we are doing? We will start from the root node. We will traverse to the half node. Right? Temperature, hot, humidity, high. Then we will predict no. So it is finding a path from root node to leaf node. A single path, not all the path. A single path from root node to leaf node. That is the option C. Follows one path from root to leaf. Sanjay got it correct. Very good. Now the next question. This is very simple. Which everyday decision matches a decision tree? Tossing a coin, choosing food using a false logic, guessing randomly, memorizing answers. It's very simple. Aparna says that it is A. A is tossing a coin. Which everyday decision matches a decision tree. Decision tree means it's if else logic, right? If else rules are there. Okay. Option B is the correct answer. Okay, fine. So that's it. The end of our session and also end of our machine learning session. Okay, so I want to remember something in real machine learning projects. Once we build a model, we don't stop here. Okay, after finding the best algorithm, we do not stop here. What we do is like we can save the model. We can save the model. We can reuse the model. We can deploy the model. Deploy the model in the sense we can add this model into any website or any mobile applications or anything, and we can create an application and we can give it to a live system to predict the values like production and that line given or not like that. Okay, there is a deployment and there are advanced techniques are there for that. You need to study either the web framework or mobile applications to what connect with this machine learning models. Okay, then there are hyperparameter tunings are there, feature engineering is there. So many new techniques or advanced topics are available in the next steps to study. So this is the foundation, the foundation here for the classification problems. Okay, so if anyone here feels interested to learn data science, if you are interested in this area to learn data science or wants go to deeper into artificial intelligence, you can definitely take this as your starting point. If you are interested in taking this learning forward, you can start exploring data science more in detail. Slowly move on to AI, like start complete machine learning, then go to deep learning, then natural language processing, then generative AI, then agentic AI, and advanced areas like that. So AI is evolving, so it will be learning will be also uh, going on. Okay, so at LPSR, we guide learners through these journeys from basic Python to AI ML projects. Okay, so you can continue learning whenever you feel ready. So today we have completed an end-to-end mini ML project. You understood the idea, built the model, evaluated it, and also we have compared the result. So this is a strong start. If interested, don't stop here. Try upskilling yourself in this area. Okay, deeper into AI. So before we wrap up today, I will share the feedback form and please take a moment to fill the feedback form. And meanwhile, if you have any queries, you can ask or you can put it in the chat box. Okay, please fill the feedback form, and if you have any queries, please put it in the chat box. We will be updating that. We need to check it with the resource person because the resource person is our CEO. So it will be updated. No worries. The next schedule will be informed before. Okay. Certain data set we have to train model with different algorithms, just one algorithm. Different algorithm. We check with different algorithms, not just one algorithm. Okay, can you suggest some projects other than our assignment for our practice? Yeah, sure. We have seen one website, no, Kaggle. You maybe remember that, Kaggle. Kaggle is the best learning platform for machine learning, deep learning, and natural language processing, etc. In Kaggle, we have learning materials available. Also, in Kaggle, we have basic harder level projects. Okay, in that, if you are interested, you can go to Kaggle. Then in Kaggle, beginner level projects. You just start with the beginner level projects. If I specifically say a project, you can try out disease prediction. It's very interesting one. Okay, disease prediction. Sometimes old algorithms will be there in the Kaggle. You can try out what you studied in the webinar or in the session, and also you can explore those said in the Kaggle also. Disease prediction is one other classification. From symptom, it will be predict disease. Then if we go for another, like if you are interested in NLP area, you are trying to study NLP, you are interested in such areas, then you can go for review prediction, like whether the review is positive or not. Amazon review analysis are there, Flipkart review analysis are there. Different types of problems and dataset with the code is available in Kaggle. So Kaggle is the best source for your learning. You got an idea, right, Krish Gupta? Okay, fine. So, okay, if no more questions, we can wind up. Before that, I will show our LMS. I think you can see your LMS with all the sessions. Remember that for our sessions, you have quizzes to attend. You need to attend the quizzes, and our entire case study is there in the reference material. The data set we used, and also the complete code is there in the ML case study in basics under basics, and also quizzes are there for machine learning, for SPM, and for KNN and decision tree, one quiz are there. So it will be available in the KNN session, both decision tree and KNN quiz. And the task is mentioned in the today's head, that is day 9. This is our task. Okay. In that task, you will find a PDF file. In that PDF file, you can download that PDF file. If I show your PDF file, this is the PDF file. Okay. So here the link for the dataset is there. You read the problem. I am not going to explain it because you also need a skill to understand the dataset, right? So what you want to do is you go to the dataset, try to understand the dataset. Then the objective is mentioned here. You need to try SVM, KNN, decision trees, classifiers, at least 3 algorithms. Okay, if you are interested, you can also try any other algorithm after learning it. It is not mandatory. The minimum requirement or minimum objective is that whatever we studied in the SPM and KNN decision tree classifiers, you need to work out in that data set. All the processing steps you need to try out, and you need to train the model, you need to print the confusion matrix, you need to print the accuracy score. And what we want to do is that you need to submit either IPNB file or the PDF file. I think when I introduced Collab, I have shown you. You can download it. The Collab file, you do the activity, you do the task, then go for file, then download IPYNB, this one. Okay, download it and upload it in the LMS. Okay, or you can give a print here. When you give a print, it will be coming in the PDF format. Okay, either IPYNB or PDF format, you need to upload the file in the dataset, and the guidelines are clearly mentioned above at the top. The guidelines are clearly mentioned. Duplicates, getting duplicate submissions, resubmissions, and also the pass marks, etc. So clearly read the instructions and submit the task. And also support mails are also given there. If you have any queries on machine learning, you can post to me. Okay. And also we will be having the next session about RAG, but it will be on January. And by this, we are winding up with the machine learning sessions. I hope this session helped you understand how ML works from practical perspective and inspired you to learn more. Okay, so thank you all for your participation and enthusiasm throughout the series. Okay, so happy learning and all the best for your ML journey. Thank you.